Hello everyone. Today we are going to listen to an expert who is doing seismic survey day in and day out in different parts of the country. It is none other than Dr. Satish Kumar, scientist from National Geophysical Research Institute of CSIR India. Satish Kumar has completed his MSc in Marine Geophysics from Andhra University. Then subsequently he completed his PhD in Westmania University. His research topic is on study of geophysical signatures for delineation of ore bodies as well as groundwater resources in different geological formations of India. He is an expert in delineating shear zones and fracture systems, especially by making use of MASWA, that is multi-channel analysis of surface waves. So, who has done commendable work on MASWA is with us today to highlight you the technique of MASWA, especially with the different case studies. Thank you. Let us hear him now.
Hello everyone. Good morning, very good morning. My name is Dr. K. Satish Kumar. I'm working as a principal scientist in National Geophysical Research Institute under the Council of Scientific and National Research Institute. Today's topic is seismic methods and particularly MASW for the application of geotechnical application of geotechnical engineers and structural and civil engineers. So how my MASW can be utilized for the geotechnical engineers, how it can be utilized, and how can the problems issues can be resolved from the using this geophysical technique MASW. So before going to the details of the MESW, first you would like to, as a geotechnical engineer, what is required, what they required for the construction and any major constructions. Actually, before the near subside exploration is mostly geotechnical applications is mostly less than 30 meters. It's common geotechnical application less than 30. Why less than 30 meters is the why you call it? It is a called as engineering bedrock. Engineering bedrock that mostly you'll be looking for the less than 30 meters. So that is called the bedrock. Bedrock. And another thing is where is the weathered zone, whether within the 30 meters, where are the weathered zones, very loose zones and saturated zones. We have to be very careful about the as a geotechnical engineer. And also we have to look for the what are the fractures kind of things also very most important. The fracture what is so we have to take very carefully while concentration of these things. What are and other thing is cavities and any man-made cavities any natural cavities while during construction or after construction also you may find out natural cavities. And also subsidence is one of the major problem for the geotechnical engineers to understand the various subsidence is happening or subsidence happening and what are the causes for the subsidence to understand the structures about related by the subsidence area. So if subsidence area is present in the any major construction site, it is a problematic. So we have to be avoid the subsidence areas whenever subsidence areas. Another thing is that what be this method MSW can also we can use of the P wave or refraction and seismic collaboratively can give the input for the elastic modulus. Elastic modulus also we can derive from this using MASW technique. So it is a we can derive from the shear velocity, shear modulus, and Young's modulus, and bulk modulus also. These modulus also you can do. So to get the design parameters, these are the one of the basic input parameters of the engineers. So where we have to apply? Where we have to apply these things? Where your engineers can be applied? Majorly major power projects. Another thing is the IREP projects. Why IREP is the integrated renewable electrical for wind, solar, hydroelectric. For major projects, it required these kind of structures. How we can lay the structure. How what do design precautions we have to take, and also major bridges, and also railways mostly in the Jammu Kashmir areas to kind of construct the railway bridges. It requires the geotechnical assessment of the subsurface, and also major dams also we require these kind of surveys. Apart from this major restrictions and earthquake-prone areas under the urban planning, how to take the mitigation studies of the earthquakes. Also, this method is well populated for the understanding the subsurface. So basically seismic techniques and seismic techniques. These are the traditional methods of geotechnical downhole continuation, downhole surveys and cross-hole surveys and cross-hole tomography and seismic refraction and seismic refraction tomography. Nowadays, all dam projects, seismic refraction tomography mostly the people are using for the to a high resolution data set, high resolution. And cross-hole tomography also well validated. It is a borehole geophysical technique. You can give the coverage also. Coverage is less, but you can give the high resolution images. And also now MASPA also it is part of the service. Now it is one of the advanced technique to easily understand the subsurface without drilling any borehole information. As well as know that well logging also one of the to understand this seismic velocities of the subsurface well logging. Other thing, two things are SPT and generally geotechnical engineers they can rely on the SPT and CPT. These are the what is the MASPA MSW? It is a non-destructive geophysical technique. You cannot destruct any subsurface. Easily you can understand subsurface up to 30 to 40 meters. Easily we can reduce the subsurface strata column with your fine resolutions. So what we'll get in the MASPA? If we are using MASPA techniques, what you can easily understand this. So we can get the 1D shear velocity as well as 2D shear velocity and 3D shear velocity of the subsurface. Easily understand that. And also we can get the average velocity. So we can usually estimate the average velocities of the subsurface in 1 meter to 2 meters up to 30 to 40 meters. Easily we can average velocities. We can get to design any spectra. These velocities are average velocities are most required for the engineers. Another thing is what are the shear velocity we are derived. It is directly proportional to the stiffness of the soils. And also the N value on engineer body is one of the parameter engineers can be used for this N value. The N value also we can easily can understand from the up to 5 meters N value we can reduce. And also predominant frequency of this soils and also amplification of the soils also we can easily derive from this from the shear velocity what you are getting. The most important factor, all geotechnical applications, it is the liquefaction potential. Whether loose soil formation, the liquefaction potential is the most important factor of safety is more important. We have to understand that where are the liquefied zone, it should be take care of the liquefaction potential zones. So these are the generalized table of the understand the formations with respect to the velocity. The right hand side, what we are seeing the seismic velocity of different rocks. The shear velocities, the less than 180, we can call it as soft soil, and less than 180 below, we can call it a very loose soils, and also 180 to 360, you can call it stiff soil. If it's rock and basalt and granite rocks, we can call it a very hard rock formation. These are velocities are greater than 1500 meters. So what we can understand this. So once you get this survey, you can easily understand the formation, what kind of formation, the compatibility of formation and stiffness of the formation easily understand. Apart from that, the NEHRP and National Earthquake Hazard Reduction Program, they have given you one standardized table. The standard table is can be used for you can classify the soils. You can classify the soil, which kind of soil, which kind of rock it is. If less than E or less than 180 meters, we can call it a class C. And apart from over that D, E, B, C, you can classify. If it is the rock engineering, whatever the rock, A, B, C, the engineering bedrocks. These are the engineering bedrocks, the hard compact rock. We can lay the any foundation over this formations. So engineers easily understand what is the rock formation, compatibility and compatibility and the rock formation. So now we're coming to the actual details of the MASW technique. Actually, MASW means it is a multi-channel analysis of surface based multi-channel. Actually, previously it was a SASW. It is a single channel surface based analysis. Later on, it was modified at multi-channel. So multi-channel means multi-sensors. Multi-sensor, you can use a multi-sensors and can, it is first introduced by Park and 1999 it was introduced. And also it can give the subsurface values with respect to stiffness up to the 1D, 2D, 3D up to 30 meters. And MASFA, MASW, actually there is two data acquisition methods is there. One is the active, another is the passive method. The active method, what we are using, we are artificially creating the signals, and passive we can generally we are recording the natural waveform from the coming from the Earth surface. So these are the two things. One is the active MASFA, another is the passive MASFA. I already discussed this. So before going to MASW, first we have to understand what are surface waves. What are the surface waves? Why am I talking about surface waves? Actually, waves are two types: body waves and body waves and surface waves. Actually, body wave, all exploration geophysics, all traditional geophysics, people are all concentrate on the body waves because P and S wave they concentrate to P waves. So they're the most first instant waves, and P waves we're concentrating. You can see the left hand side, it is one of the traditional seismograph, and there's a now the vertical and horizontal and east-west component. Here what the surface waves, what the energy, you can see that why surface waves are, this is a high amplitude waves, and also short period is high, so it can give the destruction mode. That's why you have to concentrate on the surface base of the energy. Now coming to the exploration GFS in the right hand side, why surface? Most of the any exploration section, you can see the 90% of the energy is from the surface base. Or other 10 to 20%, 10 to 20% consider of the body base, P base, but people only concentrate of the P base. But in the MASW, we should be concentrated on this surface based energy. The blue color polygon, what you are showing is that this is the surface energy window. Or we have to consider, so we have 90% of energy we are utilizing here, because people are more concentrated on all exploration geophysics, only consider P and the first break of this section. But we here in MASW, Park has they has done the beauty of this method is to understand what are the unknown waves, what are the unknown energy we are utilizing, and we are it interpreted as a useful, meaningful information. So why we are considering it is a basic how we do it. The surface are generally two types: one is relay waves and log waves, and it is retrograde motion, and it will during it the destruction is more to the surface waves. This is a simple thing. Why surface waves of MASW we are using? So we had a one property, that one property is we has the property. Other property is dispersion. Why dispersion is more important property is utilizing it. Different frequencies of seismowaves travel in different speeds and propagate at the amplitude, the wavelength, the width of the wavelength is proportional to the depth of the formations. So shorter wavelength you can give the shorter formations, and longer wavelength you can give the deeper information. So you can easily deduce the both shallow information as well as deeper information within the same method. We can easily understand the different kind of formations. And also we are using P wave energy. There is a hidden zone problem is there, but here there is no hidden zone problem. We can easily understand the where is the fish, where is the weak zones, we can easily identify from this method. So this is the actual basic dispersion, working on dispersion principle. But the parameters, what are the acquisition parameters, are the more important to acquire, to record the surface waves energy. What are this? The first one is the source, and second thing is the what receivers you're using, and also recorder, And also group interval, what group interval you are using, the more important, and offsets, and also spread length. While if you want to map the deeper features, deeper things, you have to include the spread length. And also sampling interval, also one of the more important. The sampling interval, what 0.25. If you get the shorter objectives, you can identify the shorter things. You can have to sample length should be very less, and also record length also we have to increase some of things. And record length is more you have to use it for this passive, and record length is short. Record length you are using for the active source. So sources, coming to the sources, actually sources are actually MASW using the hammer. Hammer is one of the source you can use. Wavedropper also some of people are using. Also Vibrus is also one of the source that people can use for the sources. The receivers, what you are using, they are using the geophones for the receiver. Generally 4.5 geophones, had geophones only we are using. For some of people 10 Hz also you can use, but 4.0 is the more we are using. So recorder is Geode, 24 channel recorder we are using. The group interval, generally group interval, what is the group, the spacing between group interval means the spacing between the two sensor. We are using the 1 meter and 2 meter, and mostly 1 to 2 meters. And the offset mostly you can take to 5 to 6 meters only offset we are using. If you use longer offset, we can miss the surface energy. So after why I'm focusing is after doing many experiments of this offset thing, we can fit the shorter offset to 5 to 6 meters, or maximum 10 meters. You can use, you can get the good zero elasticity energy. So this is the actually real field pictures of the my MASW, how we are doing. So the right hand side is this is the, you can call it sledgehammer. This is another hammer. The cages 8 to 10 cages generally we are using for this hammer. This hammer having one hammer switch that can give the signals to the the geode. This is the yellow box what you are seeing, the 24 channel recorder geode, this one. And this is the what is the yellow cable, it is the communication cable from the geode to the system. And also the black color, what you are black color the figure, this is the hammer cable. The hammer cable directly connected to the this recorder. This is the another cable. This is 24 channel takeout cable. You see, this cable is consist of 24 takeout. 24 takeout means each connection it can give the polarity of the each geophone. These are the spike geophone. Spike geophone. It is you see the here is the spike they are doing. They digging the to the ground, coupling with the ground, the geophones. So we are for one geode we are using 24 geophones for the connection. After that, what will get the data signals it received from the easily online we can easily understand the what are the what is happening in the during time. Here you can see two recorders connected to the 48 geophones, and here this is the noise also. We can easily record the noise also. So what are the actual record after shot? What is the record also we are using? We can online every we can easily understand the whatever the noises we have to in filter also. While during acquisition itself we can filter some of the noises. So actually this is the pictorial picture of the how we can lay that. So generally this is first shot. This is the 1 to 24 channels, 1 to 24 channels. After taking first shot, what will the water complete spread will move forward 1 meter or 2 meter based on the interpreter, what are the observer what requires of the objectives. And shot point 3 it can move further. Shot point 4 it can move further. Like that we can cover the like CDP CMP common midpoint technique. We can acquire the all the complete entered data sets. Here the right hand side you can see that this is the layout of the geophones what you are seeing. Here generally we are using two kinds of geophones. It's a frequency of 4.5 hertz geophone. Why 2 kinds of geophone? One is the spike coupled with ground. Another thing is some of the residential areas we cannot able to couple the geophones. That's why for that we can use the base plate. It can couple easily. It has three legs. It can you can place like wide table or tabletop like that. You can place the all geopins in a line, and we can record the signal from the source. So the left hand side, what we are using, this is the typical diagram of the 49 shots of the setting up the geophones. So if you want to do coverage of 49 meters of the ground, we have to take layout of 72 meters. Then only you can get the 48 meters of the, because it is CMP technique. You can use you can get the midpoint of the sensors. Easily you can record it. Here, this is the setup, and this is recorder 1 and recorder 2 and recorder 3. This is the hammer, and it can connect to the controller. Controller can directly connect to the PC. So this is the first cable, and second cable, third cable. First cable, first instant 1 to 24 will be connected, and second instant it connected to 2 to 25, and third instant it connected to 3 to 25. Like that, it will cover the whole survey, or whatever the here kilometers. Also we have done 2 to 3 kilometers. Also we can easily like reflection kind of thing. But here parameters are different, and sensors are also different, and the source also different. So this is the one of the this is one of the see sir, how we are hitting the ground. So after hitting 4 to 5 shots, we'll move forward. For each shot, we'll take to 4 to 5 shots. If energy resists in first shot, even though we'll stack all the energy. We stack the one first energy, second energy, third, 4 to 5 shots. We stack all the energy to enhance the signal to noise ratio. So that is the hammer source, and this is the one of the vibration sources. We have facility. These sources. One is the mini vibrator. Another is the big one is the major Hemi 50. What will happen if you want to get the depth information 1 to 2 kilometer, you can use these two vibrators. We can use that to understand the subsurface. And also we have in this we can generate P and S wave also. There is the S wave source also there. We have to switch over the S wave source, S wave recorder, and P wave recorder source only. We have to change that. And then the left hand side, what we are seeing there on the circle, this is the string geophones. String geophones is there. We can use 10 geophones instead of 1 geophone. You can use 10 geophones. Why? Because to enhance the signal to noise ratio, 10 geophones you can use at about a single point. This high coal exploration and oil exploration, we can use this kind of setup. It's one of the we can use for the MASW also. So this is the actual pictorial picture how it can work. 2D seismic survey, how it went. First 1 to 24 will connected. There is the offset of source is there, vibrators. You can see how it is working in the, how it is sensing in the ground. After first instant, what will have? Two geophones. The spread is forward. First two geophones will be inactive. It will go to another 3 to 26. After that, again it will go to 4 to 27. Like that, it will forward. Sometimes people will use for the one geophone, one short interval. Sometimes 2 short interval. That it depends upon the interpreter. So now this is the acquisition parameters. What we discussed, how acquire that. So now, once we acquire the good quality of data, processing it is very easiest way, and we can easily understand the what we recorded easily. But during most of the things, the interpreter, what we have to do is, during acquisition itself, we have to filter some of the unwanted signal, like super power line signals and all. Even though if you culprit, if it is culpritated with the unwanted signal, we can process we can nullify those signals from in the during processing. Actually, in MASW processing involves the nearly three major steps. One is the generation of D-specific curve, another is the extraction of D-specific energy, third one is the inversion, and fourth is another stacking up the all the 1D velocities to get the 2D velocity. See, this is the first recorder one, recorder two, recorder three. In the same recorder, what we were previously what we have presented here. Just a minute. This one, this is the actual raw record, or right hand side or raw record. You can see that when you where sir, it is 0 to 100, 500, all those unwanted signals here in the bottom and top also. But after that, as an interpreter, what we have to do in this processing. So in the first instant, we have muted all the body waves. The first arrival, the P waves, whatever we have muted, we have taken, because the what are the P waves we are recording, it is unwanted for this MASW. And also, and the next we have done the bottom mute. Bottom mute, these are the multiples and unwanted signals. This also we have muted all these things. These are the window. What are the window we are saying, the 25 to 500 tapper 150. So this is the window of the high energy of the surface waves. This can be used for the processing. After, even those we have to use some of the band pass filter, high pass filter, and FK filter also. We can available many commercial software. Surf size is one of the thing, and many part size, many commercial software available, and so we can some of the purchase, we can purchase, and some easily codes also available. You have available codes also, easy codes also available to download to understand all these things. So you have to apply all the filters if you require. You can apply the filters to nullify that. But filters, most of, as per my knowledge, filters don't use much filters for it. It will be nullify the actual signals of the subsurface. Once you record that the surface wave, what we record as, we have to generate the dispersive curve. This is we are generating the dispersive curve. Actually, the dispersive curve, what is it? It is a function of the phase velocity and the frequency. It's a function of the phase velocity and frequency. Actually, here the interpreter, you should use his brain to understand where are the multiple. Actually, in the dispersive, here I projected it is a clean dispersive curve. But the clean dispersive curve cannot be available some of the areas. So what will have, it is culminated to multiples. So mode 1, mode 2, mode 3. Here the basic funda is, we have to pick the fundamental mode of dispersive curve. Here, see, the dispersive curve is the exponential. This is the fundamental mode of dispersive curve. We have to pick all the energy. We have to extract all the energy. Here the dominant frequency is 10 to 12. Dominant frequency 10 to 12 dominant frequency. So we have to catch these dominant frequency. Some of times what will happen, the dispersive come appear here. Sometimes he will appear here. Here modes of things, mode 1, mode 2, mode 3, mode 4. So we have to be understand which one is the signal. After processing multiple times, then only we understand where is the exact signal, where it is, and also we have to compare with the existing borehole geology. Then only we can come to that what are the strata. First we understand before interpreting what are the strata we are expecting from the subsurface. So after extracting this energy, whatever the white dots, 1, 2, 3, 4, the white dots, this energy will be converted into it. We have to invert this energy. Once we invert this energy, we can get the zero velocity. The 0.9 times of the Rayleigh velocity is the zero velocity. That is the beauty of this MASW. So if we invert the surface energy, we can get the zero velocity. So the blue color, what we are seeing in the blue color, it is the shear velocity with respect to the depth up to 35 meters. We are seeing. You can see that here. First most thing is here high velocity, and here he is in the low. You can see to 22.5 to 20 frequency. Here we are identifying the low velocity. Below the high velocity, here a high velocity, below the high velocity where we receive the low velocity. These kind of thing we can easily you can actually the inversion can be done by least square method, and also Mount Carlo technique also can people can using for the inverting the dispersive energy for that. And also while inverting also here we have to consider the signal to noise ratio also. We have to consider what is signal to noise. Signal to noise ratio more or less equal to 1, then it can get the good inverse curve. It is all the 1D shear velocity. This 1D shear velocity, all the 1D shear velocity we have to stack per the 2D shear velocity. We have to stack per 2D shear velocity. Then you will get the 2D shear velocity of the image with respect to the depth. You can see that the first layer, what you are saying is the low velocity layer up to 10 meters. After that, moderate velocity. After that, the bed depth, the 30 meters. The, the 30 meters, what we are seeing in the 30 meters, it is a compact more than 500 meter per second we are receiving. So what we are saying is that this is the one of the massive kind of thing. Massive means it is a compact rock, compact formation. We can understand that. So engineer can be utilized also up to below 30 meter. There is a high compact formation is there available for this understanding of the engineers. So this is the acquisition and processing of the MASW, what we have learned. Now, what we are doing? What are the case studies? How we can identify this um, heterogeneous actually here I classify many. I have 20 years of experience. I have done many engineering sites, but here I have classified few things only: soils and where are the soft rock and sedimentary and hard rock terrains. I have on the each, and I have one of each one examples. So first thing is alluvial furnace. Generally in alluvial regions in the Indo-Gangetic plains, in the Indo-Gangetic plains, what we are expecting in like Lucknow, Kanpur, those areas, Uttar Pradesh, there's a very loose kind of formations, and coastal areas also very loose kind of formations we are observing. And also in the soil, within the soil column, we are observing the various varieties of soils with variation of the grain sizes and also grain sizes also. So in the grain sizes also we can identify. So what we generally will target of this is, you can see that these pictures in the right hand side, this picture here the first 5 meter, this 5 meter, this is a high velocity layer. It is a 300 to 400 500 meters. It's unsaturated layer. Below that we can find a saturated layer, low velocity layer. So these kind of low velocity should not be present while constructing any major engineering construction. We have to take care of that. We take care of these kind of things. Below that again if, high formation part, maybe this is the water saturated and groundwater level, groundwater zone also. The groundwater zone will convert with highly saturated zone. That we have to take, take care of these kind of things. Here also you can see the layer 2. Layer 2 is very compact, high velocity. Below that again we can see the very low velocity. After 20 meters you can see the dense and compact soil. So engineers we have to should take care of this low velocity layer, and um, below that here we are observing the what of the below that high velocity layer we observed is below that. Here in this year complete this zone is measured with very low velocity layer. We have to rule out these kind of structures. We observed that any engineering side we have to rule out, and we have to take other precaution measure for this kind of regions. And that if you go to take the soft rock, Himalayas region, there's a sedimentary formation, and also in sedimentary formations also we can understand the high. Generally, in most of the Himalayan region, we have what we understand is high velocity layer is over the low velocity layer. You here see the big zone here. See this scene weak zone. So if these kind of features are we are observed these kind of features, we should be very careful. This is called the weak zones. So we cannot retain what are the any structure over this this bed. And also we have can observe vertical zones, weak zones also we can observe. Come see here completely massive rock, massive the velocity is more than 1000. It is completely hard rock. But within the hard rock there is a seepage. There is a seepage also. Weak zones are identified here in this area. Next, I mean, coming to the hard rock terrains. The hard rock terrains generally it has a high velocities, generally basalts. This is one of the basalt area. So it is completely it is a basaltic and granite high velocity. But even though if you understand the any lineaments and faults, you can see this is completely it is a high velocity of hard rock. How much this is 1500 to 2500 velocity is a high zero velocity. Even though within the high velocity we have observed very low velocity 300 500 completely saturated joint potential. It is used for potential groundwater zone, but engineering purpose, engineering by drug kind of thing, we have to avoid this kind of thing. This is here the right hand picture here. See, this is the contact and lineament zone. We have you can understand this. This is so this completely high velocity hard rock terrain. It is a very low velocity. So this is the one is the contact zone, and fall and lineaments and fall kind of things also we can easily identify. Now coming to the cavern zones and limestone areas. Generally in limestone areas, what will happen? The formation of caves are it is occur. What to understand the cavern zones, the MASW can be easily. You can see the blue color. What you are seeing, this is the cavity zone. Cavity zone. It is a hollow. It is a hollow. So if it is moisturizer velocities or below then below the this air filled cavities. And also we can easily map the bottom of the cave, bottom of the cavern zone, and top of the cavern zone also we can easily identify from the MASW. These are one of the practical examples what we have done. The known cave zone we have identified to understand the lime. However, the massive limestone zone, it is massive limestone. It is a below it is the quartzite is there. Below the hard quartzite is there. So now coming to the another example. This is another example of Himalayan region. It is the application of the combination of active and passive. Actually, the active generally we can get the most velocities we can do 30 to 40 meters depth. Or above that, we don't rely on the it gives also we don't rely on the depth more than the 40 to 50 meters. So we only will get the better information. High resolution images only can get 30 to 40 meters. But what about the below 40 meters? Or what is the zero velocity? Can you utilize? So we can utilize passive. So in the using passive technique, we can get up to 100 meters. We can map the subsurface up to 100 meters using passive. If you combine both passive and active, if you combine both active and passive, the green color what here progressive, so you can get the as well shallow information as well as the deeper information. But deeper information, what you are getting the 40 to 50 meters, not much like 30 to 40 meters or resolution. As we know that if we go to deep, the resolution will be reduced. Resolution will be reduced. But it is an advantage to get the rough idea of the subsurface up to 100 meters. We can use both combination of active and passive. So now I would like to conclude this talk. Actually, the talk MASW application for the geotechnical engineers. MASW can effectively map the heterogeneous of the subject for the various geotechnical applications, dams and bridges, and heavy engineering construction areas. So, thank you, sir.